Okay, hi everyone. This is a video on matrix multiplication. I thought I'd better do a video for this one because it's something which, on the surface of it, it looks complicated, but it's not that bad. It really isn't. It's one of those things actually you get used to and you get really quick at doing. A bit like learning your timetables. At first, it seems like really tricky, but once you're doing it all the time, you wonder what all the fuss was all about. So I'm going to show you what matrix multiplication is all about. Now, from the first exercise, you probably learnt, I hope you learnt, that matrices come in different sizes. So I'm just going to make one up. 2, 1, minus 3, 4, 2, 7. Yeah. Now, the other thing that's worth saying is you can give the dimensions of a matrix, just like you can give the dimensions of a rectangle. You know, they're all kind of rectangular. And we tend to always write rows, then columns. Now, this has 3 rows go across, yeah, and 2 columns. So the dimensions of this would be 3 by 2. That's going to come in really handy in a moment. Now, if you let that be, I don't know, matrix A, and do underline your matrices. We underline them for the same reason we underline vectors. Please do underline it. They'll always be bold in the exercise books, in the textbooks, sorry. You should always bold, or if you can't bold, underline them. Let's say B was instead of a different dimension, 1, 3, 7, 2. In the last exercise, you discovered that A plus B isn't possible. Why isn't it possible? It's not possible because they are not additively conformable. That's the phrase. I'll even write it down for you. Additively conformable. Now, two matrices are additively conformable if and only if they're exactly the same size. And because this one has 2 rows and 2 columns, this is only a 2 by 2, and hence you can't do a 3 by 2 plus a 2 by 2. Now, all well and good. And, you know, it probably seemed ever so simple doing that in the last exercise. Well, matrix multiplication is more complicated. In fact, these two, if you were doing A times B, they would be conformable. They would be multiplicatively conformable. And that's what people find really strange first about matrix multiplication. So let me take these two matrices right from the top. And I'm going to do a matrix multiplication on these two matrices. But before I do that, I'm going to make this remark, and I'm going to do it all in colours, yeah? First, let me write down in a flashy colour. Sorry, I'll get rid of those arrows as well. You can see the rows and the columns. Remember, columns stand upright, rows were like rows in a, you know, an A4 sketch pad, an A4 pad, you know, the rows go across. Or rows on a, you know, a stadium, rows of seats. Okay, so let's get some decent colours going. Let's note that if we do rows then columns, that this is 3 by 2, 3 rows and then 2 columns. And if we do rows then columns, this is 2 by 2. If you want two matrices, if you want to multiply them, the first thing you must check is that they are multiplicatively conformable. Now, two matrices are multiplicatively conformable, which sounds like a very complicated phrase, but, you know, use it to sound intelligent. That's what I try and do. Why is Sorry, I'm stressing out a little bit here because once again, basically, my graphics tablet is struggling. Okay, so these are multiplicatively conformable if and only if so I'm going to write a double F there for if and only if. The columns for the first matrix equal the rows for the second matrix. Now, there's lots to say about this because this is the trouble. When we do a normal multiplication, 7 times 3, we know that's exactly the same as 3 times 7. That's known as commutativity. When you can just move the numbers around like that and swap these over and still have the same result, the reason that's true, and it's true for addition as well as multiplication, Both addition and multiplication are commutative, but division and subtraction are not, yeah? Well, matrix multiplication is not commutative. What does that mean? It means the order matters. So you have to write down the matrices, and so let's say we write down A times B, A times B. A times B is conformable. These matrices are multiplicatively conformable because we've got the same values here. If I can just circle them, if these two are the same, then you're good, yeah? The columns from the first one and the rows from the second one, then you're good. You can do the multiplication. And what's more, the size of your answer will be these two. So I know I'm going to come up with a 3 by 2 matrix. Okay, let's try and do it. 3 rows, 2 columns. Now, I'm even going to underline where I'm going to put my values here because I've got 3 rows and 2 columns. So it's going to look exactly like this one, yeah? When we do it, and I'm actually going to write down, I'm going to give myself a bit more space, and I'm going to write down both matrices next to each other because it's nice to see them next to each other. So I'm just going to rewrite down those matrices again. So we've got 2, minus 3, 2, and 1, 4, 7. And I'm going to multiply that by a totally different size matrix. Wow. 1, 3, 7, 2. Hope I haven't bunched that up. Okay, when you're doing this, I want you to look at the rows of the first one and the columns of the second one. And then to find this, just this first entry here, what you have to do is 2 times 1 plus 1 times 7. And that comes to 9. That's your first value. Now, it's up to you which way you want to go next. Personally, I'd move down 1 row here, and now I'm going to use the second row in. And I'm going to stay on the first column. And I'm going to do minus 3 times 1 plus 4 times 7. I think that comes to 25. And then I'm going to move 1 row down, and I'm going to do the bottom row times by the first column. So I'm going to do 2 times 1 plus 7 times 7. And that comes to 51. Yeah? Great. I've done the first row. To do the second row, I do exactly the same routine, but this time using the second column from my second matrix. So now I'm here, and I'm working on the top. So 2 times 3 plus 1 times 2, 8. I then go down to the next row, and I do minus 3 times 3 plus 4 times 2, that's minus 1. And then I go to the next row, and I do 2 times 3 plus 7 times 2, which is 20. And so I don't know if you can see that. Let me just write that down again a bit clearer. 9, 8, 25, minus 1, 51, and 20. And you've got your answer. Now, the clever amongst you will probably immediately ask, can my calculator do this? Yes, our flashy class whiz calculators, is there anything they don't do? They can multiply matrices for you. I just really can't remember how. No doubt there will be a simple Google video explaining how to multiply 2 matrices. Trouble is, you certainly can't depend on that because they know this trick and they always put letters in their matrices, so you have to learn how to multiply 2 matrices together, and you should learn how to multiply 2 matrices together. So let's just go over all of that once again. You can only multiply 2 matrices if this number at the end of your first matrix is the same as this number at the end of your second, and the resulting size will be this one by this one. That gives me the resulting size. And then you do row times first column, that times that plus that times that, then second row times first column, then third row times first column, so on and so forth. And then you move along to the second column and repeat the whole process again. It takes a bit of practice. You're going to have to do some practice in this exercise. That's why we do the exercise. It's good for you. Now, I want to ask you a question. That was A times B. What about if we did B times A? Yeah? A times B, we already know. Let me just write it down here. We've got space here. So A times B is that answer. How about B times A? A times B equals that. Well, B times A, that's a problem. That is not conformable. And that's because you've got, if I just write it down here, 1, 7, 3, 2. Who cares about the numbers? This is 2 times 2. That's all I care about when inspecting whether they can be multiplied together. minus 3 times 4, 2, 7. But the important thing is that this is 3 by 2. I don't know why, but it's just not letting me. I get to the side of the screen and it just suddenly doesn't want to let me write. That's so annoying. Oh, computer issues, hey? Okay, let's do this here. Okay, right. As you can see, this is 3 by 2. Always looking at numbers in the middle. This is b times a, which we're doing here. So we're going to be doing that times that. But you realize straight away, because these numbers are not the same, it's impossible. It's not conformable. Yeah. Now, if you tried to do it, I challenge you to try and do it. What are you gonna do? You're gonna do this row times this column. Okay, 1 times 2 plus 3 times minus 3, and then what are you gonna times both 2 by? It doesn't work. It doesn't work. It's because you're doing the rows times the columns. And so the rows in the first one and the columns in the second one have to be the same. Yeah. So yeah, it will immediately break down. If you ever try and do one which is not conformable, you'll find yourself in hot bother very, very quickly because it's just not possible. Okay, let's run through that again though, because it's well worth practicing. I like to use ones with crazy different sizes here. Just get used to it. And I'll be honest with you, most matrix multiplication that you'll end up doing, when I say most, I mean 98% of it in this course, will be with square matrices where you won't have to worry. You'll be doing a 3 by 3 times a 3 by 3, and the answer is a 3 by 3 because the 3's in the middle are the same, and so we use the outside 3's. But generally speaking, square matrices, when you multiply them, you get exactly the same size matrix. So most of the time you won't have to worry about this conformable width, but you never know when they're going to ask it in the exam. It's definitely part of the course. Let's do some wildly different ones. Let's do one which is like 1, 2, 7, 3. And then let's do, let's see, what is that? Okay. I'm just trying to work out ones which are going to be conformable here. Yeah, let's do one like this. Okay. So here's my matrix A. Here's my matrix B. Can we do A times B? Well, actually we can, because this is 4 rows, 1 column, and this is 1 row, 3 columns. Yeah, the numbers in the middle are the same, and the resulting matrix will therefore be a 4 by 3. So it's going to be 4 rows and 3 columns. So if you like, there's going to be like space for that many numbers, if you like. I wouldn't normally do these dashes. Personally, I don't normally draw them in. So I just wanted to give you an idea that the resulting size is going to be 4 by 3. Now let's see why it should be 4 by 3, because it only really makes sense. Okay, first row, first column. Well, that's just 1 times 1. Yeah. And then go down here, 2 times 1. Go down here, 7 times 1. Go down here, 3 times 1. And then likewise the same with the 2, so that's going to give me 2, 4, 14, and 6. And likewise with a minus 5, you're going to get minus 5, minus 10, minus 35, and minus 15. Okay, what about if we did it the other way round? It's no dice. You can't do b times a. B times a is not conformable. Yeah, so this is this conformable business. Now, straight away, that gives us a really interesting feature, one of the properties of matrix multiplication. One of the properties is that matrix multiplication is simply not commutative, even if they were conformable both ways round. And I'll show you that, an example of that as well. Matrix multiplication is not commutative, i.e. b times a doesn't equal a times b. It's possible that it might, but it doesn't always equal. B times a doesn't always equal a times b. Yeah, it's possible, but it's definitely not guaranteed, and 99.999% of the time they won't be the same. Okay, so that is matrix multiplication not being commutative. Let's actually have a look now at why we do this with matrices. What are we doing here? By the way, matrix, I believe, is it's Latin for womb, and I think it means basically that it encapsulates a lot of information in a really neat format. Yeah, that's what I think. It's like, it's holding the information. So let me show you what I mean. Minus 1 minus 2 minus 1, 3, 6, 7, 2, 5, 4. If I multiply that by x, y, z, and made it equal to, let's say, 3, 2, 7, I've actually written down a system of simultaneous equations there. Now, why have I written down a system of simultaneous equations? Well, this first matrix is 3 by 3. This next matrix is 3 by 1. Notice they're the same in the middle there, so they're conformable. And the resulting answer should be 3 times 1, just as this is. Now, why does this encapsulate simultaneous equations? Well, because when you multiply it out, you do that time, you'd start on the row and start with a column, yeah? And you do 1 times x plus 2 times y plus minus 1 times z. Well, that's x plus 2y minus z. Oh, and that should equal this number here. So it equals 3. And then we do the next row down, and we've only got one column, so we're going straight back to the first column. And that's going to give me 3x plus 6y plus 7z. And it equals the entry over here, which is 2. And then last row down, I wouldn't suggest doing these arrows. It's not what I normally do at all, but I'm just trying to show you what I'm doing. You get 2x plus 5y plus 4z equals 7. And so matrices are a lovely way of encapsulating information because you see simultaneous systems of equations like this are really, really common. We teach you simultaneous equations with two unknowns at GCSE because they're really, really common, but they're not normally just two variables. It's perfectly normal out there in maths in the real world to have a system of 50 equations and 50 unknowns. And how would we how would we deal with that? Like on a computer, for example, we would program all the values, all the coefficients into a matrix. That would be the sensible way, certainly, of displaying the information. It's a nice way of dealing with it. And then you do things like if you ever do any linear programming, you'll move into row operations and stuff like that. In fact, that is in the decision maths module, which we are strongly considering doing next year. So who knows? Who knows? Who knows? Okay, so that was just a quick kind of example of why matrix multiplication is kind of useful. Did I want to say anything else? Yes, I did. I've told you already that matrix, let's do some square matrices, yeah? Most of the time we work with square matrices. Square matrices of size 2 by 2, but more commonly size 3 by 3. And we find determinants and things like that, which we'll come on to soon. So don't worry, that's in the post. But let's have a look at a square matrix, yeah? 1, 2, minus 3, 4. Straight away with square matrices, 3, 6, 1, 0. Notice that because they're all the same numbers, you're going to end up with a 2 by 2 matrix. And let's just quickly remind ourselves which way around it goes. Let's call this one A and this one B. So we're doing A times B here. 1 times 3 plus 2 times 1, that's 5. Try and fill this in. Pause the video if you like. Try and fill it in yourself first. Shall we be daring and do it in a slightly different order? Should we do this one next? That's where you stay on the first row here, but you go to the next column. 1 times 6 plus 2 times 0. 6. Sorry for doing it in a different order. I'm just teasing you now. Now we can do minus 3 times 3 plus 4 times 1. Tell me if I make a mistake in the comments as well. I think that's minus 5. And then minus 3 times 6 plus 4 times 0. That's minus 18. Yeah? Now, that's A times B. What would have happened if we'd done B times A? Because maybe matrix multiplication is only commutative when you have square matrices. Maybe that's the case. Let's have a look. We can test the claim. 3, 6, 1, 0. Multiply by 1, 2, minus 3, 4. That times that plus that times that. That's 3 minus 18. Well, that's minus 15. It's already looking definitely not commutative, even when you've got square matrices. Yep, that's minus 18. That times that plus that times that is going to be 6 plus 24. I think that's 30. And then that times that plus that times that, that's 1. And that times that plus that times that, that's 2. and I've done it. You're probably getting crossed because I'm suddenly doing it the other way around. I'm almost doing that to torment you. First entry is always that times that plus that times that. If you want to go down to the next one, that's fine. 1 times 1 plus 0, you still get 1 in there. The order doesn't matter. You get more flexible with this as you work. But as you can see, matrix multiplication, even with square matrices, it's not commutative. It tends not to be the same answer. And that's very important. Now, note as well, I can't remember if the first exercise introduces you to this matrix. I. All the I matrices are square matrices. And an I matrix is the identity. It is the I matrix for 2 by 2 size is 1, 0, 0, 1. It is the only matrix you'll find where when you take any other matrix, let's take 3, 6, 1, 0, just as before, and you times it by I, well, you're going to get 3, 6, 1, 0 times by 1, 0, 0, 1. So we're doing loads here, loads of work, aren't we? Good. That times that plus that times that. Oh, you get 3 there. That times that plus that times that. Oh, you're getting 6 here. That times that plus that times that, you're getting 1 there. And that times that plus that times that, you're getting 0 there. Look, you ended up with exactly the same matrix as you started with. I think we called it matrix B. So B times I equals B, yeah? And the identity matrix works either side. We talk about post-multiplying or pre-multiplying. If I pre-multiply B by I, then I should be before B, and it still works out to just equal B, and I'll just prove it to you. If you post-multiply by I, if you post-multiply B by I, then that's where I is multiplied afterwards. So talk about pre-multiplying and post-multiplying, and you'll be garnering loads of respect from me when you do that. Okay, 3610. Just to prove this still equals B, doesn't matter which way round you multiply the identity. 1 times 3 plus 0 times 1, 3. 1 times 6 plus 0 times 0, 6. 0 times 3 plus 1 times 1, 3. 1, sorry. I said 3, I don't know what I was doing. 0 times 3 plus 1 times 1 is 1. 0 times 6 plus 1 times 0 is 0. And so you end up with B again, yeah? So that's why the identity is important. It's like timesing by 1 in normal multiplication. It is the element, if you're doing group theory, it is the element or the matrix anyway, which when you multiply by it, it doesn't change the matrix. So it's tremendously important, tremendously important. Okay, so that's the identity matrix. The identity matrix, by the way, for 3 by 3 matrices, I don't know if you can guess what it's going to look like, but it's going to have a leading diagonal of 1s. That's what it would look like for a 3 by 3 matrix. We tend to work with square matrices. Now,